Okay, I'm back trying to finish up another problem that I guess it's the next type of problem that would be on that worksheet 3. Really, for Unit 5, that's a really good worksheet because it kind of involves a lot of stuff. But this is what we call a two-body problem, and two bodies because there's two bodies. Not like human bodies or anything like that, but we talk about objects. We use the term body for an object, so they call it a two-body problem. Now this looks complicated because we have this object up here, which I'm going to do this as if this surface is frictionless. So if this is frictionless and you have this object hanging right here, this object is going to cause this whole thing to accelerate. So the force of gravity acting down here is going to cause this to accelerate. Since there's no friction acting back against this is going to accelerate this way. Now this problem looks complicated, and what's really cool is that I'm going to show you how to do this, and we're going to take a problem that looks really tricky and we're going to make it look really easy. Like I've seen people do problems like this. I've had kids that I've worked with before from different classes, and their teachers showed them all these complicated ways of doing these problems. And I look at them like, what are you guys doing? This is not a hard problem. It's actually a lot easier. There's a real nice, easy way to simplify this problem. So what we're going to do is we're going to look at this, and we're going to find the acceleration. We're going to find the tension in the cable. That's this cable right here that's attaching the two blocks. So we have this block right here. We're going to have the force of gravity down this way. We're going to have the tension in the cable right up here. Well, this tension here this is all the same cable, which means that this tension right here is going to equal this tension right here. So if you think about that, if we thought about just this block here, the 6 kilogram block, what we have is a tension force this way with nothing acting against it. So that tension is what's going to accelerate this block. Well, the other thing we think about is this is all one system. So it's not like the 2 kilogram block can't accelerate any faster than the 6 kilogram block because they're attached by the cable. So these have to have the same acceleration. So if we know what this tension would be, we know that we can figure out the acceleration just using F equals ma. But because of this whole system being tied together, we can't make it that easy. So we're going to look at it instead. I'm going to draw free body diagrams. So I'm going to draw a free body diagram for the 6 kilogram block. And I'm just going to start that. It's pretty straightforward free body diagram. We have an FG and an FT, or an FN, not an FT. Well, we do have an FT, it's just the other direction. So that's FN. Those cancel, I'm not even worried about them. We know it's on a flat level surface. It's not going to accelerate up or down. So the only acceleration for this block here is going to be to the right. So I'm going to have an FT that just goes right there. So I'm going to label that FT. I also have this block, and for this particular block, we have just an FG and an FT. So I'm going to have this FG here, that's going to come down like this, and then I have an FT up this way, and they're not balanced because this is going to accelerate downwards. So this is longer than this force here. The other thing we can look at, and we can kind of treat this like a third law pair, this force pulling up on this block is this cable pulling this way is the same as this force right here. So what we can look at is we can say, okay, this is all the same cable. This force is equal to that force. Those are equal. We're going to use that later on. Okay. Now, if I start throwing numbers in here, I can look at this and say, hey, you know what? 2 kilograms. My FG over here is going to be 20 newtons. So my FG is 20 newtons. Don't know my FT. Don't know my FT. I have my FG here, which is 60 newtons, which means my FN is 60 newtons. Don't need that though. I'm not going to look at that. I'm not going to write it on my free body diagram. You can if you want, but I'm not going to. Now, when I look at this, what I'm going to look at is the reason this whole thing accelerates is because my force of gravity is pulling down right here. This FG right here, that's that guy, is pulling down, and it's not just pulling the 2 kilogram block. Now, if this was free fall, we'd have 20 newtons, mass of 2, we'd have acceleration of 10 meters per second squared because it's free fall, but this isn't free fall. This 20 newtons is pulling 2 kilograms. It's also pulling 6 kilograms. So really what's happening is I'm going to look at this entire system. I'm going to look at this entire thing, all right here. And I'm going to treat this whole thing like it's one big 8 kilogram block because they're tied together. Who cares if there's a cable right there? We're going to look at it and we're going to pretend like this is an 8 kilogram block. In fact, this is really no different than having this. If I had a 6 kilogram block here tied to a 2 kilogram block here, and I had some 20 Newton force pulling like that, which really is no different than having just an 8 kilogram block pulled by a 20 Newton force. Ultimately, that's what's happening. It just so happens that there's this pulley right here that's bending the cable, you know, but we don't even have to worry about that. So ultimately what we can do is we can say, hey, you know what? This is 20 Newtons pulling 8 kilograms. So when I do my Newton's second law, I just go through and say sum of the forces equals mass times acceleration. My sum of the forces is just 20 Newtons. Nothing's acting against that. These tensions are inside the system now. So if I'm looking at this as one big block like this, there's nothing acting back this way because there's no friction. Now if I threw friction in there, I subtract off the friction, but I don't have it. So I'm just going to say 20 newtons pulling 8 kilograms. So 20 Newton force equals 8 kilograms times acceleration. And now I just solve for A. 20 divided by 8, that's going to give me 2.5. So now I have 2.5 meters per second squared. And I have my acceleration. So that's all I had to do. Again, to kind of review this real quick, you don't have to redraw like this. I just did that to show you guys. But you just look at this and go, hey, you know what? I have an FG right here. And this FG is pulling the entire thing. So use the mass of the system. That's one of the biggest problems that I see with a problem like this, is that we forget to add the masses. So we look at it and go, okay, well, my FG here on this block, the hanging block, is going to pull the entire 8 kilograms. So 20 newtons pulling the entire 8 kilograms gives us an acceleration of the system. Now, my second question was find the tension of the cable. Okay, so now if I want to find the tension of the cable, I got to choose one of my free body diagrams. Doesn't matter which one you do. I'm going to choose this one because I don't have to worry about a down and an up. I just have to deal with one force right there. So now if I want to look at just this free body diagram, just this block, I just figured out that this block has an acceleration of 2.5 because the entire system has an acceleration of 2.5. So if this block is accelerating at 2.5 meters per second squared and it only has one force that's acting on it that's not canceled out, this is my sum of the forces for that block. Now notice I changed the system now. To figure out the tension, I'm looking at the system as just this block. So now if I want to look at this free body diagram, again, that's for my 6 kilogram block, then I can just say, I'm going to switch seats real quick. So I'm going to look at it this way and say, in this case, for this here, my sum of the forces is Ft. And that's what I'm looking for. So if my sum of the forces is Ft, and I know the mass of this block, 6 kilograms, I know the acceleration, then I can just plug that in. So Ft in this case, which is my sum of the forces, is equal to mass times acceleration, which is 6 kilograms times 2.5 meters per second squared. And I just plug that in. So 6 times 2.5 is 15 kilogram meter per second squared, which is a Newton. And I figured out my tension. So we can think about that now. Does that actually make sense? Doesn't make sense. Doesn't make sense. Okay, well, if my tension is 15 newtons, so 15 newtons here, that's fine. That works because it's going to accelerate a 6 kilogram block. You can plug that into F equals ma. 15 newtons divided by 6 kilograms gives an acceleration of 2.5 meters per second squared. This Ft equals this Ft. I can think about it that way too. If this Ft is 15 newtons, you can verify it. Does that make sense? That Ft has to be 15 newtons. Well, I know I'm accelerating. I know this block is accelerating downwards. So 20 newtons is bigger than 15, which means it's accelerating downwards. You guys probably could even look at this and go, hey, you know what? If I have a 15 Newton force upwards and a 20 Newton force downwards, that's going to give me a net force, a sum of the forces for this block now of 5 newtons, 20, subtract 15, given that, calling that positive in this case. Doesn't really matter, I can call it negative if I really wanted to. But either way, we can recognize that the net force here would be 5 newtons. 5 newtons on a 2 kilogram block, 5 divided by 2, 2.5. We get the acceleration of 2.5. That's just another way to verify that your answer is correct. It all makes sense here. Now, when I chose to use this free body diagram, you could have just as well used this free body diagram and solved for the 2.5. It wouldn't have mattered. So again, it wouldn't matter. I just use that one simply because it only had one force as opposed to using two. But you can use either one. So again, this is one of the harder type problems. But if you learn how to do that, this part right here is really quick. You don't have to do this drawing here. You just look at that and go, okay, it's one force accelerating the total mass of the system, and it's a straight F equals ma. 20 newtons, 8 kilograms A, bam, you got your acceleration. This part's a little bit trickier, but again, if you just break it down into each block, it comes out pretty straightforward. The last 3 problems on that worksheet are 2 body problems. One of them I think you'll get a kick out of. Usually makes people laugh a little bit. And then the last one's just a little bit different, but you kind of do the same idea, where it's called an Atwood's machine, where it's just hanging over a single pulley. It's just the 2 blocks hanging from it. And you can use the same idea from here. The only difference is that you're gonna have to subtract off. You're gonna basically have to find the difference between the FGs, and that'll give you your net force. And of course, if you guys have any problems with it, you can always shoot me an email. Feel free to ask me questions. You can email me anytime. I just about always have my phone on me, unless it's on top of a tripod like it is right now. So, all right, I will talk to you guys soon. I'll put up a next video here pretty soon. Our next concept is going to be talking about friction and how we're actually going to calculate friction. That one might be a little bit longer, but I'll probably video that one tomorrow night or the following night and get that one posted pretty soon. Okay, you guys take care. I'll talk to you soon.